co-orbital theme.
Yeah, this talk is highly related to the previous. Collisions with large near-Earth objects can produce co-opting debris. And if the debris is less than 100 meters in diameter, it's hard to detect by traditional methods. This statement comes from this histogram where we show the number of total discovered near-Earth asteroids as a function of their diameters. And the percentage on top of each bar shows the estimated percentage of discovery. And we can see that when the diameter is less than 100 meters, our discovered object is less than 1% of the total population. Even these objects are small, they're still potentially hazardous, because from the simulation results, we find that objects of 50 meters in diameter will result in the most damage per year. Then we heard from the previous talk that the co-orbitals collide regularly and disruptly with small but numerous meteoroids, and there are clouds of nanoscale dust or gas particles released in such destructive collisions. These clouds of dust can interact with the solar wind electromagnetically and create large perturbations in the interplanetary magnetic field called the interplanetary field enhancements, for short IFEs. And here I show a plot of an IFE example with the magnetic field profile and the plasma profile. The highlight region is where the IFE is. We find that it is mainly magnetic structures. It has the enhanced field strength, the band field lines, and pressure enhancement during this event. But if we look at the plasma data, here I show the solar wind velocity, solar wind proton number density, and the temperature. We see that the plasma and the magnetic signatures are uncorrelated. This indicates that the magnetic structure was built slowly relative to the thermal speed. And in the superposed epoch analysis, we find that during this event, if we normalize by the ambient value, the velocity has a small, about 0.5%, but statistically significant solar wind slowdown on the trailing edge. This is where we believe the solar wind part is, and on the other side is the dust cloud is. And this indicates that momentum is transferred from the solar wind to the dust. With multiple spacecraft simultaneous observations, we can improve our understanding of the magnetic geometry of this event. Here is an event seen by 5 spacecraft, and this plot I show the magnetic field projections in a coordinate system where X is the direction of the solar wind flow from right to the left, and Y is the ambient magnetic field direction, and Z is then opposite to the convection solar wind electric field. In this plot, in the upstream region, the magnetic field drapes around the IFE, while the center of the IFE is here. And this again indicates that the momentum is transferred from the solar wind to the dust. Therefore, the dust cloud can move out at nearly the solar wind speed in the some gravitational well. And in the downstream region where we believe the dust cloud locates, we see that the magnetic field has been bent in the direction of the electric field, and we suggest that this is due to the different mass-to-charge ratio of the dust from that of the solar wind protons. Okay, in the 1980s, with the PVO observations, we find that the IFE clustered in a certain longitudinal range. In this plot, each sector covers 30 degrees in longitude, and the radius of the sector is the local IFE daily rate. And we can see that this is the highest rate region, and it is the region where the orbit of Oljato lies upstream of the observer. And because Oljato has a small inclination relative to the orbital plane of Venus, the transverse distance between the two orbits shown here is less than the cross-flow radius of the FE. Therefore, we define the whole sector as the FE as the Oljato sensitive region, and we suggested that any disturbance created in this region will be swept by the solar wind to the downstream and detected by the spacecraft. And here we show the FE rate as a function of the phase difference between Oljato and Venus, or observer, yeah. And inside the sensitive region, we see that there is a clear association between the FE occurrence and the phase difference. The FE rate is high when the Oljato is nearby, and outside the sensitive region, the rate is generally random, except for very weak correlation in the region where the phase difference is small, and I will mention that later. Based on these two plots, we confirm that not Oljato itself, but the co-opting material, both leading and lagging the Oljato, is responsible for these FEs. Similar to the analysis performed at 0.72 AU, we survey the ACE and the wind data at 1 AU and find this FE occurrence rate distribution. And we find that between the range from 195 degree to 215 degree, the FE rate is high. So we are looking for the Oljato-like source in this region. We compare the elliptic plane passages of known NEOs in this region and find that the co-opting material of asteroid 138, 175 is the most probable source. Here I show the plot, the orbits of the asteroid, and this is in the elliptic plane, and this is in the transverse plane. It has two nodes, descending, ascending, and because its inclination is about 5 degrees, so in most of the parts, when the orbit lies upstream of the orbit of the Earth, the transverse distance from the elliptic plane is larger than the cross-flow radius of the FE. So here we suggested two sensitive regions for this asteroid, and we assume that all the FEs detected in these two sensitive regions are potentially related to the material accompanying the asteroid. And here we show the FE daily rate as a function of the phase difference. Inside the sensitive region, when the asteroid is nearby, especially within 72 degrees leading the asteroid, the FE rate is high. While outside this sensitive region, the rate is generally low and random, except again we see a weak correlation here. From the previous talk, we know that due to the gravitational scattering perturbation, the material will be scattered across the orbit of the parent body, and this weak correlation seen outside the sensitive region may be due to this co-opting material scattering. And if we can weigh the FEs by balancing the pressure gradient force with the solar gravity. More details of this will be covered in our poster. And from this method, we find that the FEs have mass from 10 to the 6 to 10 to the 12 kilograms. Therefore, the most of the responsible co-opting material is of tens of meters in diameter if they are stony material. This material then will be too small to detect by the traditional optical method from the Earth. And also from this plot, we show the FEs associated with Oljato, that's the gray bars, and the FE mass associated with asteroid 138, 175, that's the black bar. We find that the co-orbitals of Oljato are generally more massive than those of the asteroids 138, 175. This is reasonable because Oljato is at least 3 times larger than the asteroids 138, 175 in diameter. So we expect the larger co-orbitals. And we do a simple calculation, and we find that to create the FEs at the observed rate at 1 AU, tens of thousands of objects would co-opt with the asteroid 130 and 175. And this will only comprise only 1% of the original mass of the parent body, but it will greatly increase the impact hazard. We can find the temporal evolution of the co-opters by comparing the early observations with the modern observations. We've done this for the Oljato, and we see this plot before. And as Professor Russell said, we suggested that the gravitational spread is the main mechanism for the loss of co-opting material of Oljato. Well, for the asteroid 130 and 175, by comparing the rate between infrared observation and the modern observation, we find that the decay time scale is about 15 years. And if we use the interplanetary flux model and calculate the collisional decay time, it's about 43 years. And we think these two numbers are consistent. Yeah. So we suggested that for the asteroid 130 and 175, the disruptive collision is the main mechanism for the loss of the co-opting material. So for summary, we can identify interplanetary objects with diameters of tens of meters when they collide with meteoroids. Nanoscale dust particles released in these collisions perturb the solar wind and create the interplanetary field enhancements. We suggested that co-opters of Oljato and 138, 175 produce many IFEs in their sensitive regions. And by studying the IFE occurrence spatial distribution, we can infer the spatial distribution of the co-opters. And by studying the mass of the IFEs, we can infer the size distribution of the co-opters. And by studying the IFE rate inside the sensitive region, we can find the temporal variation of the co-opters. Well, our technique does not identify the location of the debris until it is destroyed, but it can get the telescope where to point. Yeah, that's it.
Okay, we have time for one very brief question. Any questions? Otherwise, thank you.